Hello friends, welcome to my channel. Let's have a look at problem 1971. Find if path exists in graph. In this video, we are going to explain two methods or solutions. The first one is based on traversal, and the second one is based on union find. First, we'll read through the problem statement to digest the requirement, and then we do the analysis and comments, and finally we share the code. First, let's look at the problem statement. There is a bidirectional graph with n vertices, where each vertex is labeled from 0 to n-1 inclusive. The edges in the graph are represented as a 2D integer array called edges, where each edge is represented by two nodes ui, vi. So it means that there is a bidirectional edge between vertex ui and vertex vi. Every vertex pair is connected by at most one edge, and no vertex has an edge to itself. We would like to determine if there is a valid path that exists from vertex source to vertex destination. The task is the following. Given edges and the integers n, the source and the destination, return true if there is a valid path from source to destination, otherwise return false. So here are two examples, which are very simple. So you can see in example 1, 0 and 2 are directly connected, so the return is true. While in the second example, there are two connected components, and the source 0 and the destination 5 are not connected. Therefore, the output is false. So for the constraint, I would like to draw your attention to the size. So n is bounded above by 2 times 10 to the power 5. So this number is actually a decent large number. So and the others are some additional assumptions for consistency and for extra assumptions, like there are no duplicate edges and there are no self edges. So with that said, we are ready to do the analysis and the comments. So here, this problem actually can be reduced to the following, right? So we want to determine if the source and the destination are in the same connected component. So with this in mind, let's do the following comments. So this problem, check path existence, is actually a very routine question. We could use breadth first search or depth first search to do the check. And also we could use union find to find connected components. For the latter, as the edges are bidirectional, we could conclude two nodes are path connected if they lie in the same connected components. So this comments actually also contain the methods we're going to present. So below, we're going to demonstrate the two lines of methods. For breadth first search or depth first search, so there are many ways of writing the code. So we're going to use an iterative format for details or for understanding. Well, for the union find method, we're going to use path compression and union by find as routine practices in view of the problem size given by this number. So with that said, we are ready to do the coding. So first, I'm going to write a solution based on traversal, right? So for this, I'm going to first create a graph. So here, let me do this, create a graph. So this is not absolutely necessary, but we want to cast this problem in the mainstream of a graph problem, right? So it's graph, it's collections, so default dictionary, I'm going to use a set as the default container. So then for UV in edges, so notice that the graph is a bidirectional graph, so we're going to do this, graph U, so add V. It means that V is a direct neighbor of U. So similarly, we want to claim that U is also a direct neighbor of V, right? So this finishes the task of create a graph. So next we want to check path existence. So for this, I'm going to write a hyper function. So define path check. So here we have a source and we have a destination, right? So then we want to check if these two can be connected. So then I'm going to use a auxiliary set to do the traversal. Here I'm going to use depth first search. Let's see. In other words, I'm going to use S as a stack. So then this is the basic iteration of while loop for while S. So first, let's get the node we are currently visiting. And then we are going to check if node equals destination. So we are done. So we just return true. Otherwise, we want to add this node to the auxiliary. It means that we have already visited this node. And then we check the neighbor for vertex in a graph node. And then we're going to check if vertex not in aux. So this is a filter, right? Then we're going to append this to the top of the stack. Afterwards, if we haven't got anything yet after the while loop, so we're going to return false. So with that said, we finished the second step. The third step is check with the problem logic, or writing the problem logic. The problem logic is to check if the source and the destination are in the same connected component. Let me change a little bit. No, okay, let's keep this because we want to see path check. So here, let's copy so that we do not make spelling mistakes. Source and destination. This forms one solution format, which is based on traversal. So here we're using a depth first search. So here, if you pop 0, it corresponds to breadth first search. So with that said, let's first do a check. Yeah, this is for a special example. That is, I guess, yeah. So now let's look at the generic case. Yeah, it passes all the cases. So with that done, now let's look at the second method. So let me copy this function signature and this annotation part. So I'm going to change this one to be version v1. And now I'm going to use a unified method, or well known as disjoint set. So this is actually regarded as a data type. So let me first make some preparations. So first, preparation for unified. So here I'm going to initialize two dictionaries, I, and rex. So here I is the roots is going to track for a node its parents or its root. So for I in range m, right? So originally, so I will set the parents of I to be itself. So the size to be 1. So for I in range m. So typically people use a list here for tracking this root. So here we still we can use dictionary. So for easy retrieval of information. So this is the one part, and then we're going to implement the disjoint set ADT methods, that is unified. So I'm going to implement the find method first. Let's see, given the vertex or index, so let's find its root. So here, let's introduce a result variable called result, and then we're going to do a while loop. This is very standard. While result does not equal to roots result, and then basically what we want to do is that result equals roots result, right? And then here we want to do before this a path compression. So this way it accelerates. So here we apply the roots here and apply roots here, right? So there are other formats of doing the path compression, so like using a for loop. So, but here let's content our steps with this. So once we exit this while loop, result will equal to roots of result. So we just need to return result. So this is the find method. So here we are using find with path compression, right? So this is a very interesting trick or technique. So next, let's implement the union method. For this, first let's get the root. So let's use find I, find j. From here, you also notice that when we first implement the find method. So next, we are going to check if root I equals root j. If they are the same, so we do not do things. Otherwise, we do some root researchment and rec modifications. So let's check if rex root I is larger, right? Let's see, rex root j. Then in this, we are going to set the root of root j to be root I, and then increment the rex of root I by that of root j. So this is simple, right? So let's see, roots of root j equals root I, and then we are going to copy this line. Let's see, and then we are going to change this to be increment by the rec of root j. So here you can interpret the rex as the size of the corresponding representation of that cluster. So otherwise, so we do in the reverse direction. So let's do this. We're going to set the root of root I to be root j, and increment the rec of root j by that of root I. So that's it. So here, let's see. Let's make an annotation. So this is the union by rex, right? By rec. So with that done, so we finished the implementation of the union find methods, and then so we are going to do the problem logic. So for this, we just do for UV in edges. It means that UV are connected. Then we just do union, right? Do UV. So this is the problem logic. Next, we're going to do the return. So we want to check if the source and the destination in the same connected component or in the same connected component. It corresponds to see if they have the same roots, right? Because the roots is the representation of the corresponding cluster or connected component. So here, let's do a source equals find destination, right? So this forms the second solution format. So here we can do a check first. Yeah, it passes one example. Now let's look at the generic case. Yeah, it passes all the generic cases. So with that said, actually up to now we finished the two methods. One is based on traversal and the other is based on union find. So actually we have two playlists for traversal and for union find method. So we actually practiced quite a lot for this kind of problems and for these two lines of methods. So you are welcome to check out the corresponding playlists at our channel. So with that said, I guess that's about it for this specific problem, and also it's the end of this video. Thank you.